Hello, my name is Michał Ślęzak and I work at AGH, University of Science and Technology in Krakow, Poland, and I'm going to speak about magnetic properties of nickel oxide antiferromagnetic overlayers on iron 110. So the overview of my presentation, I will mainly speak about nickel oxide overlayers on iron 110, but I will also show very briefly some results concerning isostructural system, namely cobalt oxide 111 on iron 110, and also at the end I will show you some fresh results concerning individual ferromagnet, antiferromagnet nanostructures. So my introduction concerns purely ferromagnetic system, namely iron on tungsten 110. So magnetic anisotropy in this system strongly prefers the in-plane orientation of magnetization, and we expect such thickness-induced in-plane spin orientation transition, which happens as the thickness of iron is increasing, and magnetization is changing from in-plane 1-10 orientation to 001 orientation, so the bulk is the axis of iron above some critical values of transition. And similar transition can also be induced in a uniform thickness system, for example, by changing the temperature. And now I switch to results. First, nickel oxide on iron, the main part of the presentation. The idea was that let's cover iron 110 with antiferromagnetic nickel oxide overlayer, and let's try to observe, to induce temperature-induced spin orientation transition in both ferromagnetic and antiferromagnetic component of the system. And also we expected that perhaps we will be able to document such thermal hysteresis of the transition, and that would allow us to stabilize one of two possible orthogonal in-plane orientations of antiferromagnetic spins. That was the idea. So we used X-ray absorption spectroscopy, specifically X-ray magnetic linear dichroism technique in Solaris synchrotron in Krakow. And if you take a look on absorption spectrum of nickel oxide around L2 absorption edge of nickel, you see these two characteristic peaks of intensity. The ratio of these intensities, called RL2 ratio, is commonly treated as a kind of fingerprint of or probe of orientation of magnetic moments of antiferromagnetic nickel oxide. And when we take a look on absorption spectrum of nickel oxide at 300 K and at low temperature, you see we have some small but significant XMLD effect, and from that we can conclude that we have indeed a temperature-induced spin orientation transition in not only in iron, which I do not show here, but also in antiferromagnetic nickel oxide. And we may think about in-plane magnetic anisotropy of iron here on the left side, as characterized with magneto-optic Kerr effect. So you see the characteristic twofold nature of in-plane magnetic anisotropy is directly reflected here in the magnetic anisotropy of antiferromagnetic nickel oxide, as measured with angle-dependent XMLD technique. And another question: what happens when we apply small external magnetic field? So we used XMCD to be sensitive to ferromagnet, and XMLD again to be sensitive to orientation of antiferromagnetic moments. And let's now focus only here on this black curve at the bottom. So as you see, using very small external magnetic field, around 500 Ersteds only, we reorient the magnetic moments of antiferromagnetic nickel oxide, and it shows the strength of the exchange coupling between ferromagnet and antiferromagnet, as normally without, in the absence of ferromagnet, of course, one would need Teslas or tens of Teslas in order to change the magnetic state of isolated antiferromagnet. And from that we can also conclude that we have rotatable nickel oxide spins. Rotatable in this case means that any change of magnetic state of iron either induced by external magnetic field like here or by change of temperature, will force also the corresponding change of orientation of magnetic moments of antiferromagnetic nickel oxide. And that leads me to the main result of my presentation. So let's focus here on these red curves, 90 angstroms thick iron film, XMCD temperature dependence, and when we are at high temperature, it's magnetized along 1-1 in-plane direction. When we cool down the system, it switches at some point to 001 in-plane orientation, and then we have to heat up more in order to come back to 1-1 orientation. And so we have this expected thermal hysteresis of transition. The most important thing now is to take a look what happens with XMLD, what happens with orientation of nickel oxide spins. And you see they rotate from in-plane 1-1 orientation to 001 orientation at low temperature. And again we observe this interesting temperature window in which, for example, here around 250 K, we can stabilize one of orthogonal in-plane orientations of antiferromagnetic spins, and we can switch between these two orientations in a field-free manner just by changing the temperature for a while above this temperature here or below this hysteresis here. And one may ask, what about magnetic domains in the system? So we made use of X-ray photoemission microscopy microscope in Electron with the help of Professor Locatelli group. And as you see, XMCD image shows magnetic domain pattern in the neighborhood of spin orientation transition border, and this magnetic domain pattern is directly imprinted into the magnetic domain pattern of antiferromagnetic nickel oxide overlayer. No additional domain pattern is visible inside these single domains here. And another question, can we tune the switching temperature of nickel oxide spins? And the answer is yes, but we have to be much more precise in tuning the thickness of ferromagnet and also tuning the magnetic anisotropy at the interface between nickel oxide and iron. So that is the sample that we prepared for that purpose, and briefly the example, the result. So XMLD versus temperature. So you see we are able to tune the switching temperature of nickel oxide spins in relatively wide temperature range. Importantly, it covers also room temperature switching here. Now I switch to cobalt oxide 111 on iron 110, so the system isostructural with nickel oxide and iron 110, and here are absorption spectra of cobalt oxide around L3 absorption edge this time. So we had two sample regions, 50 and 200 angstroms thick iron films, so before and after spin orientation transition. And when we measure XAS spectra on these two areas, they are at room temperature exactly identical as they should be, because we are a bit above null temperature of cobalt oxide. When we cool down the system, it's better to magnify these plots because our XMLD effect is small, and you see at low temperature black and red are significantly different, so we have small but significant XMLD effect. From that, again, we can conclude that spin orientation transition in iron induces also the spin orientation transition in neighboring cobalt oxide. Interestingly, when we apply field cooling procedure, so we cool down the system in external magnetic field, forcing the magnetization of 200 angstroms thick iron area, forcing it to be aligned with its hard axis. Then when we are at low temperature, you see spectra measured on both sample areas are perfectly the same again. And this means that it's a magnetic state of iron above null temperature, which is a decisive factor determining the orientation of antiferromagnetic frozen spins at low temperature. And this is done here for two orthogonal in-plane orientations. One can of antiferromagnet, one can also do something similar for two collinear orientations, namely for parallel and anti-parallel orientation of interfacial antiferromagnetic spins. And this can be done, for example, by cooling down the system in one of two possible remanent states, positive and negative. As you see, in this way, we can choose specific interfacial orientation of antiferromagnetic spins here and here, and also it leads to the change of the sign of shift field of the exchange biased hysteresis curve, as you see here and here. So we may speak in this way about kind of memory effects on frozen antiferromagnetic spins. And I also would like to show you that similar experiments we can perform on individual ferromagnetic, antiferromagnetic overlayers. So what you're going to see here is the movie, low energy electron microscopy movie, recorded during the annealing process of 5 atomic layers of iron grown on tungsten 110 single crystal. So we now raise the temperature, it's here, and at some point you will see the start of formation of the wetting process, the formation of islands and nanostripes on the surface, and further you will see, as you see now, the evolution of their sizes and shapes. So the important thing here is that process we can stop in the experiment immediately and also at any stage, simply by turning off the heater. And later, such self-organized iron nanostructures we can cover with homogeneous nickel oxide overlayer, and again using photoemission beam microscope we can follow magnetic domain pattern of individual nickel oxide iron nanostructures. So here is some very fresh example of our recent experiments. So as you see, magnetic domain pattern visible in this ferromagnetic component of our nanostructure is directly imprinted into the antiferromagnetic component of the nanostructure. And another interesting region of the sample, here we perform measurements for two sample orientations, two geometries, but not going into details. When we magnify some interesting region, then you see this characteristic closure domain pattern visible in iron is also reflected in the XMLD beam image. And having these two orientations, we can propose such non-collinear in-plane magnetic configuration in antiferromagnetic component of our nanostructure. And this leads me to summary of my talk. So I showed you in the main part of the presentation possibility to field-free switch the antiferromagnetic spins of nickel oxide in nickel oxide iron bilayers, and also I showed you how we can play with kind of memory effects in frozen spins of cobalt oxide in cobalt oxide iron bilayers, and at the end I also showed you that also we can perform similar experiments in the laterally nanostructured objects. Such nanostructures were imaged with Professor Locatelli group in Trieste. And with that, I would like to thank you very much for attention.